Hello, my name is Ethan Rodriguez Hernandez, and today I will present our work titled Structure Property Relationships in 3D Printed TPU Auxetic Structures, Mechanical and Acoustic Characterization. Auxetic structures are materials or structure characterized by a negative Poisson ratio. This means that, unlike conventional materials, they can expand laterally when they are stretched and contract when they are compressed. And because of this unusual mechanical behavior, auxetic structures have attracted attention for applications such as impact protection, sensors, energy absorption, and acoustic materials. This project, we wanted to study the behavior of these auxetic structures made from TPU, the thermoplastic polyurethane, focusing on both their mechanical and their acoustic response. For the methodology of this project, we 3D printed 3 triangular auxetic lattice structures with 3, 4, and 5 layers using TPU. First, we perform an axial compression test to characterize their deformation and determine their Poisson ratio. And as shown in the graphs on the right side of the poster, the structure exhibited the expected auxetic behavior during compression. For the acoustic characterization, we used an experimental tube with a 2-microphone measurement setup. Sinusoidal measurements were performed at different excitation frequencies. First, using the empty tube as a reference, and then with each specimen, we made the measurement. Instead of reporting a coefficient, we compared the measure response of each structure against the empty tube reference. For quantitative comparisons, we only consider the direct measurement region from 100 to approx more or less 321 Hz, below the conservative direct sampling limit of 337.3 Hz. Now, looking at the acoustic results, we can see that the effect of the auxetic structures was strongly dependent on frequency. Across most of the analyzed region, the difference from the empty tube reference were relatively small. However, we found some important localized changes. At approximately 254 Hz, the 3, 4, and 4 layer specimens reduced the relative acoustic response by more or less 0.71-72 decibels, respectively. The most important result occurred at 303 Hz, where all the structures produced a reduction close to 2 decibels. The 3, 4, and 5 layer structures produced reductions of 1.96, 98, and 94 decibels, respectively. The response map shown here also help us visualize that this reduction occurred consistently among the 3 configurations. However, an interesting result is that adding more layers did not necessarily produce a greater acoustic reduction. For example, at approximately 169 Hz, the 3 and 4 layer structures increased the response by around 0.71 decibels, while the 5 layer structure remained closer to the reference. So we did not observe a monotonic relationship between the number of layers and the acoustic response. This suggests that the behavior is not controlled only by specimen thickness or laying count, but rather by the interaction between the excitation frequency and the structural configuration. In conclusion, these 3D printed auxetic structures show a measurable mechanical and frequency-dependent acoustic behavior. The largest acoustic reduction was found near 303 Hz, where all 3 configurations produced a reduction of approx 2 decibels, with the 4-layer structure reaching the largest individual reduction of 1.98 decibels. These results show the potential of 3D printed auxetic structures for further investigation in acoustic applications, while also showing that their performance cannot be explained simply by increasing the number of layers. Thank you for your attention.